right by you. The Max lives right by you.
What are you doing?
He sold you out. I said, well, she does live a long ways away. She lives right by me. I'm like, oh.
Yeah, but Max
I mean,
is
I rode
way
with my
outside.
mom brought me here, so technically.
It's her fault. Her fault. Okay, let me see your. All right. So anyway, so what's this 3? 3 was the midpoints. So to do midpoints, you just go in your subinterval to the midpoint, then to the curve, and that's the height of your rectangle. So this one would be a 0. This one, we would go up to this dot right here. Oh, Skylar, I said that wrong. It's right here is the top. So then it goes there to there and down. And then your midpoint here is 0, so it would go to there and across. And then here's your midpoint, so that would go to there, and so it would go there, and then over. And then here's your midpoint would be there, so that would be there to there. And those would be your midpoints. So 4 you weren't sure about, is that what the question mark there is?
Yeah, the trapezoid.
Okay, so we can do that. So then, and when you write it out, so it would be f of, and this is what's going to be really key today is this pattern thing. So it would be f of your first midpoint would be what? -4, and then they're 2 wide, plus f of -2, and then they're 2 wide. And I was mostly looking at your pictures, but to be honest with you, this is way more important. I mean, you got to be able to draw the pictures, but you've got to be able to write this out, okay? We've got to be able to write out this thing here. Height times width, height times width, height times width. The height of these, or the width of these, is 5 minus -5 divided by 5, so that'd be 10 divided by 5, so the width is 2, so that's how we know our width. Yes?
Sometimes I didn't know, like, when it was below the x-axis like that, you don't go, you just go across and like that's just 0?
Yeah.
You don't
Yep.
go like down to it or anything?
Where at?
Do you ever go down?
Here?
Yeah.
No, okay, here's what you do. You either go to your left edge, or your right edge, or your midpoint. And we'll talk about trapezoids in a minute. But you either go to your left edge, your right edge, or midpoint. Okay? And then from there, you go to the curve. Right? And wherever the curve point is, that is the top of your rectangle. And then you just draw across. So here, the middle is right here. So you go to the curve, which is there, and that's the top of your rectangle. So it's right there. Go to the middle, go up to the curve, and then that's the top of your rectangle. So when you're over here, you go down to the curve, and then that's the top of your rectangle. Right? You ignore it. All the rest of the curve doesn't matter. The only thing that matters is at that point where the curve is. And then you just go across. And that's your rectangle. Okay? So on, there I got to close this. All right. So okay, so 4 is that, you want to do 4 on that one real quick? Okay, so what was 4? 4 was the integral from -5 to 5 again, and it was how many trapezoids? 5 again. Okay, so again, the width is still going to be 2, so here's our subdivisions, like so, okay? All right, now when you do a trapezoid, the difference on a trapezoid is you go to both edges of the interval, and then you go to the curve, right? So on a trapezoid, you go, and it doesn't matter which way. Just think of a normal trapezoid. A normal trapezoid would be if the curve was up here, and you go to the left edge, here, you go to the right edge here, and then you connect it. So let me say that again. You go left edge to the curve, you go right edge to the curve, and you connect it every single time, right? Left edge, right edge, connected. Now, it looks like a trapezoid when you do that. But sometimes if it's up and down, it doesn't look like trapezoid. So what you do is you go left edge of the interval to the curve. You go right edge of the interval to the curve, and you connect it, right? That's your trapezoid. Now, it's not really a trapezoid. It's actually 2 triangles, right? But it doesn't matter. Your formula for a trapezoid will still work. It'll be 1/2 f of negative 5, which is this y value, and it'll be negative, plus f of negative 3, and then times 2. That's your first trapezoid. Okay? Even though that's positive and that's negative, it doesn't look like a trapezoid, doesn't matter. That's what it looks like. Okay? It's not a very, I didn't draw that line very well. So it'd be that area and that area. Okay, next trapezoid, you go left edge to the curve, you go right edge to the curve, and you connect them. That looks like a trapezoid. That one makes an actual trapezoid. But it doesn't matter. It's still the same formula. 1/2 f of negative 3 plus f of negative 1 times 2, right? And then, of course, you need to get those numbers, plug them in, you know.
Wait, so what it connects to the 2 dots right there?
You always connect the dots at the curve, right? Every time you do. Okay, let me say it again. Left edge to the curve, right edge to the curve, connect it. Left edge to the curve, right edge to the curve, connect it.
So when I connected it, I got like.
Use the numbers off the graph.
So that's your first.
Left edge to the curve, right edge
To the curve, connect.
So right
That's
there.
that. Connect. Right. So now you're going to your next subinterval. It's 2y. So left edge to the curve is there. Right edge to the curve. Draw your line. Draw it up. And connect. There you go. There's your trapezoid. Okay, next one. Left edge to the curve. Right edge to the curve, which is actually right at the x-axis. Connect them, which this time makes a triangle. But that's okay, right? And it's just a trapezoid where one of the bases is 0. Okay? Next subinterval, left edge to the curve, which is right there. Right edge to the curve, connect them. Makes another triangle. Left edge to the curve, right edge to the curve, which is on 0, makes another triangle. So out of that whole business, of those 5 trapezoids, only 2 of them, only one of them actually was a trapezoid, right? I mean, only one of them was an actual trapezoid, right? The others were triangles and kind of a pair of triangles, but it doesn't matter. It doesn't matter, okay? The triangle formula still gives those areas when you add them all up. All right, any others on there? Maybe 10 or 17, maybe one of those, or 16. Yeah. So let's do one of those. Let's pick one. So what was one? A midpoint? Was one of them midpoint?
No, right.
Okay, doesn't matter. Okay, so
10 was trapezoid. 10 was 7 was
10 was trapezoid. Okay. This is it right here? Oh, perfect. Okay, so, oops. So, you wanted, what was 7? Which one? I don't care. Did you trapezoid or right? Trapezoid? Okay, so at number 10, they wanted to do the integral from 1 to 7 using how many trapezoids? 3. So 1 to 7, so that's 7 minus 1 divided by 3, right? So that's going to be 2. So they're going to be 2 wide, right? So the total width is 6, and you're going to divide it into 3. So that's going to be here to here. Oh, whoops. It's going to be here to there, and to there, right? Okay, so we're going to go, so there's 1, 2, 3 subintervals, right? So that's the most important thing is you divide it up into your subintervals. So from 1 to 7, so we're looking for this area, right, from 1 to 7 right there. So first trapezoid, you go to the left edge, you go to the right edge, you connect, right? Now you didn't have to draw these, right? You didn't have to draw these. So, but let's just, because we seem to be questioning a little bit on the drawing. Left edge here, right edge here, connect it. Left edge here, right edge here, connect it. There's your 3 trapezoids, right? Didn't have to draw them, so all we really had to do was to just do the, but you had the graph right there, but what I often do is if I don't have to graph them, I still draw my x-axis, I still look at my x-axis so I see what I got. So what am I going to have? I'm going to have 1/2, what's my first trapezoid? F of 1 plus F of 3, right? F of 1 will be this y value. F of 3 will be this y value, right? Those are my two bases of my trapezoid times my width, right? Next one will be 1/2 F of 3 plus F of 5 times 2. So I don't really need the picture. I want you to be able to draw trapezoids and right rectangles and so forth, okay? Now, number 7. So Skylar, you asked about number 7, so let's look at that. Number 7, the same thing from 1 to 7. How many subintervals? 3 subintervals. So again, they're going to be 2y, right? So where's your first right edge? Right here. So you're going to go to your right edge and you're going to draw there. You're going to go to your right edge, draw there. You're going to go to your right edge and draw there. And there are your 3 right rectangles, right? But we didn't need to draw them here. All we really needed to do was what? Where's my right edge? F of 3 times the width, 2, plus F of 5 times 2, plus F of 7 times 2, right?
So when you do right edge, you're always going to the 1.
You always go to your first right edge, right? I always say that. I always say, where's my first left edge? If I was doing lefts, my first left edge is at 1. And then 3, and then 5, right? And I won't go all the way to 7 because that's not a left edge. Where's my first right edge? Well, if I'm starting at 1, my first right edge is 3, right? Because of the width is 2, right? So you always think that. Where's my first right edge? Where's my first left edge? Where's my first midpoint, right? If we were doing midpoint, this would be, we just started at 2, right? We'd add F of 2 times 2, F of 4 times 2, F of 6 times 2. Right edge will always include the last point, and not this one. Left edge will always include this one, and not that one. Trapezoid will include them all. Okay? All right. Now, yes, the other day, because it's exciting and I don't want to shortcut this. All right. So, I guess, hang on here a minute. Maybe squeeze that in.
How exciting.
It is. It is. Okay. All right. We'll do that Monday. All right. So here we go. Ready? Oh man. Okay. Now I hate to build it up too much because then it always gets disappointing. So, but in your notes. A lot of we're going to write a lot of stuff today. You're going to have to hang on to your hats. It's kind of tough on a Friday, but you know. We won a big basketball game last night, so we're all really excited. And so that just adds to it.
We'll get you more excited after this basketball.
Hey, this is a pretty good day. I mean, in the last 12 hours, we already got to go to state and I give this calc class. I told them, we thought about staying, Emily, you weren't here, we thought about staying because of the weather in Omaha or in Lincoln, and I said, I've got to get back for this calc lecture. We've got to muddle through and get through this weather. All right, so we risked our lives, so here we are. So, Riemann sum. We said yesterday, I'm not sure if I spelled that right. I think it's E-I or, no, it's I-E. It's I-E, okay. Riemann sum. All right, so Riemann sum, we said yesterday, is just adding up rectangle areas. R for Riemann, R for rectangle. Riemann sum is adding up rectangle areas. Okay?
You need to fix the 3 plus 1, right?
Yeah, I do. It should be -1, but that's fine. All right, so let's talk about what it would look like if we, in general, wrote out a left sum. So you were just talking about that. So let's write this out. So in general, a left sum is the first left edge, which would happen at x sub 0, right? We said in the Riemann sum, we start our left edge x sub 0, then x sub 1, then x sub 2, then x sub 3. So left sum is going to be f of x 0 times delta x plus f of x1 times delta x plus, and you might say to yourself, can't you just factor out the delta x? You could, but we're not going to do that because, at least not yet, because I want you to look at this and see rectangle areas. I want you to see height times width, height times width, height times width, da 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 da. Now, left edge always stops one short of the far right edge, like we were saying, so that's why it's f of x n minus 1, right? And a right edge, of course, is going to start where? Your first right edge is going to be x sub 1. So f of x sub 1, delta x, plus f of x2, delta x, plus dot dot dot, f of x sub n, delta x. Now, notationally, that's just a nicer one, right? Because it starts at 1, it ends at n, and what you're going to hear me say later is, you know what, if somebody in their class, Cesar, I think, said, well, why don't we use trapezoids? Because they're better, right, than lefts and rights, the approximations are better. That's true, but if you're going to do a million of them, who cares, right? If you're going to do a million trapezoids or a million rectangles or whatever, you can get as accurate as you need to get if you're going to do a whole bunch of them. Matter of fact, somebody in their class said, well, you know, if 1,000's good and 10,000 be better and 100,000 be better, what would be the best? Right? I mean, an infinite number of rectangles.
So we're going to have to do the limits with these.
How do we do derivative, right? 2 points. If you get really close, that's good. Getting a little closer would be even better. But what did we do to actually find the slope at 1 point? We let that h go to 0. We let the 2 points actually become 1. Well, it's very similar. It's very similar, right? 1,000, 100,000. Okay, that's where we're headed with this today. Now, midpoint. Let's just call the first midpoint M1. Now, technically, while you write that, I'll write this down. Technically, the midpoint formula is a mess because really the midpoint would be x sub 0 plus x sub 1 divided by 2. It would actually be that. But that just makes things really a mess. So I'm just going to call the first midpoint M1 and the next one M2 and so forth. So we stay away from midpoint if we can, just because you got to find that midpoint. It's not always easy to do. Okay, well, it's easy, but it's just messy. And again, if we're going to do 100,000 of them, why not just do right rectangles, right? Because the notation just looks easier and they're easy to find, and we'll just do that. Okay. But anyway, so that's a midpoint sum. So those are all Riemann sums. So these three are all Riemann. Okay. Those are rectangles. And then we got our trapezoid. And our trapezoid, T sub n trapezoids would be 1/2, and then it'd be f of x0 plus f of x1 times delta x, plus f of x1 plus f of x2 times delta x. And then the last one would be 1/2 f of xn minus 1 plus f of xn times delta x, right? So it's just adding up the trapezoid. But you can look at that and you say, yeah, I see a trapezoid. There's a trapezoid there. There's a trapezoid there. There's a trapezoid there, right? Dot, dot, dot is all the one we put. Okay? So that's just your general, that's what a left sum, right sum, midpoint sum, trapezoid sum looks like. You don't need to draw a graph to be able to do that. Right? If you know how wide your interval is, which you're going to, because what you're doing is approximating an interval. So your integral is going to be from somewhere to somewhere, from A to B. So you just do B minus A divided by N, B minus A divided by how many subdivisions you have, that's your width. So once you have your delta x, now you can subdivide your interval down, and then your right would be your first right, and then the next right, and the next right, and the next right. I mean, right? So you can find all those values, and so you can just plug them in, right? You can just plug them in and write it out. Okay? Not bad at all. Now, problem is, if you want to do it by hand, right, 100 of them, 1,000 of them is kind of ridiculous. So what we need to do is see if we can come up with some patterns, see if we can come up with some formulas, that if we have a whole bunch of those, then we can actually find 1,000 rectangles, or 5,000 rectangles, or 10,000 rectangles, right? Okay? Without having to actually literally do 5,000 rectangles. All right. So let's go to this thing, and you may recognize this from last year. Sigma notation. This guy right here. That look familiar? Okay, and what does the Greek letter sigma stand for? It stands, the Greek letter S, it stands for sum. We use sigma to shortcut sums. Well, that's what we're trying to do. That's what we want to do. If I'm going to add up 5,000 rectangles, I don't want to have to write out 5,000 rectangles. Right? I want a shortcut. I'm going to find a pattern. That's what sigma does. So, let's just review sigma notation. So, what would this sigma right here be? And you can write them down in your notes if you want. Sigma, it always has, we usually use I, J, K for sigmas. It says I equals 1, up here it says 8, and then right here it has a 3. What is this telling you to do? What is this telling you to do?
3.
It's telling you to add 3 8 times. When I is a 1, you have a 3. When I is a 2, you have another 3. When I is a 3, you have another 3. When I is a 4, you have another 3. You keep going till I is an 8. This answer, of course, would be 24. That's really easy, right? That's really easy. Okay, what's this second one say? Sigma I equals 1 to 6. What's that saying? One plus 2 plus 3 plus 4 plus 5 plus 6. You start down here at the bottom with what I is, and it always increments by 1. Sigma can't increment by anything else. It can only increment by 1. So I starts at 1, and then becomes a 2, and then becomes a 3, and the sigma is saying sum. The sigma is saying add them up. So when I is a 1, you got a 1. When I is a 2, you got a 2. When I is a 3, you got a 3. All the way to 6, and then add them up. Okay? And then you can add them up, obviously, and see what that is. What is it? 15, 21? What's J, sigma J squared from 1 to 7 say? 1 plus 4 plus 9 plus 16 plus 25 plus ... plus 49. Right? So the sigma notation tells you where to start, and it tells you where to end. Now, sigmas don't always have to start with 1. Here's a sigma that starts at negative 2. So this is going to be negative 2 cubed, which is negative 8, plus negative 1 cubed, which is negative 1, plus 0 cubed, which is 0, plus 1 cubed, which is 1, plus 2 cubed, which is 8, plus 3 cubed, which is 27. Right? So you can start a sigma anywhere you want, but it's got to go up by 1s. So it's going to go negative 2, then negative 1, then 0, then 1, then 2, then 3. Okay, any questions about sigma notation? That's in its simplest form. Now,
So would you just take 3 times 1 plus 3 times 1 plus 3 times 1?
well, no. What do you mean times 1? There's no, this, when it's a constant here, that just said, there's nowhere to plug in an I, right? So I is a 1, then what does this equal? What is this right here when I is a 1? 3. And then when I is a 2? 3. And then when I is a 3? 3. There's no times in it. You know what I mean? It's just what is this? Okay? But when there is an I in it, or a J or a K, that's, you plug it in. Right? But there's nowhere to plug it when it's that. So it's just, okay? All right. Now, we're actually going to want to do sigmas, though, in reverse. In other words, and there's a couple rules of sigmas that are important. These are going to look really familiar. If you have a constant inside of a sigma, multiplied by some stuff, you can pull that constant out in front. Okay? And if you've got a formula with plus or minus inside of a sigma, you can split it up into separate sigmas. Yeah, I mean, you can write those down or not, I don't care, whatever. But doesn't that make sense? What's that look like to you? That's just like animals. I wonder if there's a connection. Gee, probably not. It was just random stuff. Okay, you can pull out a constant, or if you're adding in there, you can split it up into separate sigmas. That's all I'm saying. Okay, so, number 6. Okay, so number 6 here. Let's take a look at number 6. Alright, sigma 5i minus 2. So one way to do this one way to do this sigma right here is to plug a 1 in for I, right? What do you get? 3. Plus, now plug a 2 in for I. 8. Plus, now plug a 3 in for I. Plus, 18. Plus, 23. Now, one of the things we're going to want to do today, we're not going to spend a lot of time in this. The ones we do are going to be obvious because I don't really want, my goal here is not that to get you good at doing this. You actually were supposed to or should have, or at least advanced math classes used to do this, where we're going to go the other way. We're going to have this sum, and then we're going to want to write the sigma that created it, right? We're going to want to go in reverse. Well, how would you know this? Well, the way you would do this one, and here's just a little trick, but this isn't, you're not going to have to do this on the quiz, don't worry about it. But the way you do this is you say, well, you're adding 5 every time, right? Well, if you add 5 every time, repeatedly adding 5 means multiplication, right? That's what multiplication is. It's repeated addition, right? 3 plus 3 plus 3 plus 3 is 3 times 4, right? That's what multiplication is repeated addition, okay? Well, if we're repeatedly adding 5, that means we're multiplying by 5, okay? So your first guess might be 5i. Well, 5i, 5 times 1 is 5. Well, that's too big by 2. When I is a 2, 5 times 2 is 10. Oh, that's too big by 2. So how do we fix it? Subtract 2. So 5i minus 2. That's how you would come up with that pattern, how you come up with that formula. Anyway, what I want to show you is, what's that equal? 11, 24, 34, 42, 62, 65. We could have split that into 2 sigmas. We could have split that into 5i, and that one we could have just split out like that. Okay? And then minus sigma 2, right? I could have split that, right, into 2 separate sigmas. So I could have used these formulas we have up here, right? Okay, now, what would this be? Well, this would be 1 plus 2 plus 3 plus 4 plus 5, right? Everybody agree with that? Sigma I. So 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. 15 times 5 is what? 50, 75, right? 75. And then what's sigma 2? That's 2 plus 2 plus 2 plus 2 plus 2, right? Which is what? 10. And then minus 75 minus 10, 65, right? I just want to show you that these formulas, right? These formulas we have here would work. We can do that. Okay. Well, that's great and good, but what if we have 100 or 1,000 things to add up? We're not going to want to write them all out. And that's what we're talking about, right? Think where we're headed with this. We want to know, how can we shortcut adding up 1,000 or 10,000 rectangles, right? How can we shortcut that? This isn't really shortcut. It's the sigma will let us write it, but how can we actually calculate it? Okay? How can we actually calculate it? Well, that is with these formulas right here. Okay? Now, before we write down those formulas, let's look at this guy right here. What is this saying to do? 1 plus 2 plus 3 plus plus 100, right? Add up the numbers 1 through 100. Okay, now there's an old story about this famous mathematician named Gauss. When he was a genius, when he was in first grade or whatever, elementary school, he was bored because he was such a genius, and he got in trouble. And the teacher sent him to the corner and said, "Okay, go back to the corner and add up the numbers from 1 to 100, and don't come back until you're done." Thinking this would take quite a while, right? And like 2 minutes later, he came back and he had the answer. How did he do it? 1 plus 100 is 101. 2 plus 99 is 101. 3 times 98 is 101. How many 101s are there? 50. So the first number, right? So you have 100 of them, right? So 100 terms divided by 2, that's how many you have, right? That's how many pairs you have. and then times 101, right? Well, that's like n divided by 2 times n plus 1, right? If you had 100 terms, you would add it up, you would get that, right? So that was his solution, was 50 times 101. Again, so he was a genius, but that's the story. I don't know. Okay, but that would give you a formula. So if you wanted to add up the first 200 or the first 300 or whatever, it would just, if you wanted to do the first 300 numbers, 1 to 300, you could do 300 over 2 times 301, and you'd have your answer, right? So we've got a few formulas like that, and here they are right here. So you can copy these down. These will be given to you on our next quiz. We're going to call these our summation formulas. Our summation formulas. These are shortcuts for actually adding up a bunch of numbers if the sigma looks like those four. Okay, this first one, sigma c, is just a constant. So we looked at that one already. If you have c plus c plus c plus c, and you have n of them, right? It's just going to be, the sum is just going to be c times n, right? Like we did that 8 times. 3 times 8 is 24. So anytime you have a constant, so if you're doing a sigma 1 to n, whatever n is, whatever your final number is, you just multiply that times c, and that's it.
I squared.
Yeah, this is I squared, and this is I cubed. So if you have a sigma I, that's the one we just looked at. That's 1 plus 2 plus 3 plus dot 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 plus n, right? If you have a sigma I, you can find the sum by just doing this. That's the one we just talked about. If you have a sigma I squared, which is 1 plus 4 plus 9 plus 16 plus dot 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 plus n squared, then it simplifies to that. And then finally, if you have I cubed, it simplifies to that. In other words, the sum. So if we were going to add up 1,000 of those, we could do it very quickly, especially with a calculator. N would be 1,000, right? Remember this top number. If you start at 1 down here, which we don't always, but if you start at 1 right here, then this top number is how many terms you're adding up. So if this goes 1 to 100, you would have 100 things you're adding up. Okay? All right, all of this is leading towards working with our rectangles, okay, that we were doing earlier, right? What we're trying to do is we're trying to find a shortcut for adding up a bunch of rectangles. Well, sigma is a way to write a shortcut for adding up a bunch of stuff. So that's why we're going to use sigma, okay? And then these formulas are going to allow us, at least for some simple ones like I squared, I cubed, that's going to allow us to find those sums without having to add up 100 or add up 1,000 things. We're going to be able to use these formulas, and then we're going to see some patterns here that are kind of cool. Okay? All right. So let's take one like number 16 here. Okay? So number 16. So we're going to do our rules here that we just learned. So what can we do with sigma here when you got these three terms like this? Split it apart. So this is going to be sigma I equals 1 to 60 of I squared minus, and then what do we do with the 4? Out front. 4 sigma I equals 1 to 60, and then what will be inside the sigma? I plus sigma I equals 1 to 60 2, like that. Are you with me? All right, now what? Sigma I squared, we got a formula for sigma I squared right here. And in this case, our n is what? Our n is 60. So for sigma I squared, you got n is 60. That's going to be 60 times 61 times what? 121 all over 6. We'll use our calculators here in a second. On the quiz we take next week, I give you a problem like this. I'll give you the summation formulas at the top of the page, so your job will be just to split that apart and then do this and then use your calculator. Okay, plus let's do the next one. Now don't forget there's a 4 here. And then sigma I, well here's the sigma I formula right here. So that's going to be 60 times 61 all over 2. And then plus sigma 2, that's just a constant. You take the constant times n. So that's just going to be 2 times 60, right? Okay, do all that. Add that up.
So is this really even like calculus, or is just practice for what we're going?
Right. This is not sigma notation. Really, is not calculus. You're right. That is okay. What was that? What was the equation? I went from 1 to 60, and then it was I squared minus 4I minus, and then plus 2. All right. Did you get that?
What?
Now, knowing that your calculator does this is not that big a deal, right? It's in that same place where you get your integral symbol and your derivative symbol. The sigma symbol is in it. But to be honest, we're not going to do that with our calculators. I mean, big deal. Type it in, you see it, right? On the quiz next week, you're going to have to use the summation formula, have that written out, right? Use the formula, show your work, right? What's going on, okay? Because I just want you to be able to see those. But again, this is kind of like, remember we did the derivative a long way, the f of x plus h minus f of x, but it was really to try to bake into your head this idea of derivative, slope between 2 points, f of x plus h. They get closer and closer together, right? That's kind of what this is about. This is kind of the theory aspect of it. There's definitely some problems on the AP test that are like this that you have to do, where you have to understand with the sigma notation. So using the sigma notation as it relates to what we're going to see that it relates to here in a little bit. Okay, so that is the work we do with sigma. Now let's come back and let's tie that into what we're talking about here. So we did a little side trip into sigma notation. We're going to finish that up right now. So the idea is that if we had something like this, we could write a sigma, right? So we could do, so if we had 3 plus 6 plus 9 plus 12, we could write a little sigma. We could go I equals 1 to whatever. We'll figure that out in a minute. And then what would create this pattern? 3I would create this pattern. And I would go from 1 to 10, right? Because you plug a 1 in, that'd be 3. You plug a 2 in, that'd be 6. You plug a 3 in, that'd be 9. Plug a 4 in, that'd be 12. All the way to 10. 3 times 10 is 30. Now, so it's always about figuring out the first couple and then make sure it fits with the last one. So that was a pretty easy one. Okay, now, what about this one? Okay, write a sigma for this one. Now, that's a lot harder. Okay, and we could sit here and I could give you a few minutes and you'd probably come up with it, after a little while. But that's not the point. That's what we're trying to learn here. The point is this: how you write your sum has a great bearing on how easy the sigma is to write. Okay? So this is a pretty tricky sigma to write. But if I would have written this way, isn't this the same thing? Isn't that blue one the same thing? But look how much easier that is to write. If I start my I at 1, how would I write these terms? What'd you say?
I plus 1 over 2.
I plus 1 over 2. It's just very easy. I mean, look at the top numbers. The top numbers are changing. That's where the I will get involved, right? Anything that's changing, that's where you want the I, because the I is changing. The I is going to be a 1, then a 2, then a 3, right? Well, the top is always 1 bigger than what I is. But the bottom never changes, so the bottom stays a 2. Now, what is the top number on this going to be? What's the top number on the sigma? 7, right? Because 7 plus 1 is 8. But do you see how that was much easier to write if I wrote it out a certain way? Okay? Now, some people often look at this one and do this. They say, well, why not start your I at 2? Then what would be inside here? Then it would just be I over 2. And then let your sigma go from 2 to 8. And if somebody really wanted to be a smart aleck, they could start their I at 3. And then what would this be here? And go to, how many different sigmas can we write for this one? Infinite, right? We could sit here and write them all day long. We usually like to start I at 1. Just makes it simple, but you don't have to, right? And you could, sometimes it's easier to write the sigma if you start it somewhere else. So it's totally up to you, right? If you were doing it. But a lot of times we start the I at 1. Okay, so the lesson on that one is, number 1, there's infinite number of sigmas that can all represent the same thing. But also, number 2, the way you write your sum, and I'll go back to this when I said the other day, you know, you guys are going to think it's busy work when I'm making you write this all out, but it's really not busy work. It's writing it so we can see a pattern. That's what we're doing. And it's because of this that we want to do that. Okay, so here we go. So, I hope we have time. All right, so here's what we're going to do. We're going to start with the integral 0 to pi. So I don't know, start a new page in your notes, whatever, but this is connected. But this is going to be the big deal here. Now, you're going to have to try to stay with me and stop me if you need to. But it's easy to get lost in the weeds because we're going to write out a bunch of stuff here. Okay, but what are we trying to do? We're trying to write. Well, what we want to do is find the integral from 0 to pi of x squared dx. Now, we already know that that's this piece of area right here. So I'll talk while you guys are writing this out. We want this piece of area. We know by the fundamental theorem that that's 1/3 x cubed from 0 to pi. So we put a pi in. We get 1/3 pi cubed, put a 0 in, you get 0. So we know the area is going to be pi cubed over 3. We know that's the area. Okay? But remember, the whole point of this is there are some functions that don't have antiderivatives. So we have to do approximations. We have to do right rectangles. Well, 4 right rectangles is not going to be a very good approximation. 100 would be better. 1,000 would be better. Okay? Infinite would be the best. That's where we want to head to. We want to see how we can do an infinite number of rectangles. But we're going to need this notation, the sigma notation stuff to do it. Okay, that's where we're going. So let's start with 4, because we can add it. We can just do 4. Okay? So let's do 4 right rectangles. So, what do I do first? Divide it up into 4 parts, right? What's my delta x going to be? Pi minus 0 over 4. So it's going to be pi 4s, right? So, let's come over here and let's divide this up into 4s. So what's my first one going to be? Pi 4s. What's my second one going to be? Pi halves? No, did you guys not learn a thing? 2 pi 4s. I want to see the pattern. Don't write it like this. Write it like this. Right? Yes. Good. No, I expected you to say pi halves, so you're okay. All right? 2 pi 4s. What's the next one? 3 pi 4s. What's the next one? 4 pi 4s. Exactly. Yes. That's going to make it much nicer for us to write it that way. Okay, so we're dividing it up into 4. So what's my first right edge? Emily, what's my first right edge?
2 pi 4s.
No.
What?
Where's this integral start?
Pi 4s.
Starts at 0. So the first right edge So I should put a mark here and I should put a mark here. Remember, to do 4 subintervals, you need 5 marks, right? So my first right edge is pi fourths. So if I was actually going to draw a right rectangle here, it would look like that. And then it would look like that. And then it would look like that, right? But we don't need those. We don't need them. So what am I going to write here? F of pi fourths. This is why we did that homework yesterday, right? So we could do this. Times pi fourths plus F of 2 pi fourths times pi fourths plus F of 3 pi fourths times pi fourths, and then plus F of 4 pi fourths. We go to the right, last right edge, times pi fourths. That's 4 right rectangles. Now, look at that. We can write a sigma for that because we got a nice pattern. We can now simplify that sum. Anytime we have an expanded sum, we can write it as a sigma. That's what we were doing back here. We just did that here, right? We got a sum, we can write a sigma, so we can write a sum. So, we're going to start our I at 1. And what would be inside here? The only thing that's changing is the top number, right? 1 pi, 2 pi, 3 pi, 4 pi. Isn't that what I is? So it's going to be that I pi? Yeah, that's kind of interesting. Isn't that what it's going to be? But it's going to be F of I pi over 4 times pi over 4, right? Isn't that give us each term? And then the top number on the sigma is 4. So I will be a 1. This will be F of pi fourths. I will be a 2. It'll be F of 2 pi fourths. I will be a 3. It'll be F of 3 pi fourths, and so on, right? See how easy that was? Because in every one of these terms, each term's exactly the same except for that top number. 1 pi, 2 pi, 3 pi, 4 pi, so that'd be I pi. What?
Do you have to define what F is?
Well, we're going to do that right now. Yeah, oh, I see what you said. Yeah. F is always going to be that right there. So F is the x squared, right? So that's what I want to do next. Remember I said I always want to do this in F notation first? Now let's take it out of F notation and let's put it into the function. But remember German shorthand? What's F, right? If this is F of x squared, what's F of A? A squared. What's F of German shorthand? German shorthand squared. So what's F of I pi fourths? That's I pi fourths squared times pi fourths. Right? Okay? Now, what? The function. F of I, this is F right here, x squared. So F of I pi fourths means take I pi fourths and plug it into the function. Okay. Well, I want you to do this for me. Do pi fourths. So let's take each one of these and plug it into the function. So do pi fourths squared. Okay, Tim, you back him up on that. Do pi fourths squared times pi fourths plus 2 pi fourths squared times pi fourths plus 3 pi fourths squared times pi fourths. Okay, while they're doing that, we're going to do this. So what would this be if we squared this right here? I squared pi squared over 16 times pi fourths. Now a bunch of that is just constants, right? So isn't that, what's that going to be? That's going to be pi cubed over 64 and then an I squared. And what did we say we can do with the constants in the sigma? Pull them out. So we can take the pi cubed over 64 and only thing left is an I squared from 1 to 4. Right? Right? Now, what did we just learn about sigma I squared? N, and what's our N here? 4. It was N times N plus 1. No. Oh, was it? Yeah, you're right. N plus 2 is 6 all over 6. So that came from our I squared, sigma I squared formula. So 6, cancel 6. We got 4 times 5 is 20. 20 would reduce, well, let's see, the 4 would reduce with the 64, that'd be 16. So wouldn't it be 5 pi cubed over 16? Will, how you count? Did I do something wrong? Oh, it was 2n plus 1, wasn't it? You're right, not n plus 2. It was 2n plus 1, so what is that, 9? So this 6 should have been 9, right? Isn't it 2n plus 1? It's n plus 1. Oh, n times n plus 1 times 2n plus 1. Okay, all right. So 3 would go into there. Okay, so I did that wrong. Okay, so we end up with 15 over 32.
Yeah.
15 pi cubed over 32.
Yeah.
And that's what you got when you work. So when Will worked it all out here, when Will worked out all 4 of those rectangles, now let's keep in mind, what is this? What is this number? The area of 4 right rectangles. It's easy to get lost in the weeds here and forget what we were doing. We were doing the height times width, height times width, height times width, height times width. We were doing 4 rectangle areas, and it came out to be this number right here. Okay? All right. Now the actual area we know is this. Right? This area should be bigger. Right? What's pi cubed divided by 3? Or hit control enter on this, give me a decimal.
14.5.
Okay, now do pi cubed divided by 3 and hit control enter. Okay, so the actual area is 10 point something, and here we got 14 something. Well, doesn't that make sense? They'd be over approximate. These right rectangles would be too much, right? So this was 4 right rectangles, but what we did it in the blue was easier than what Will did because he had to type in all 4 of those, right? We were able to just use this little formula here, right? This summation formula, we got the same thing, right? Now it's going to come in real handy right now because guess what we're going to do next? Okay? Yes, Will, you will not have to type in 100 rectangles because we won't have to, right? We can do what we did down here. Now, this is going to go pretty quick. I'm not going to draw the whole picture and everything, but what will be different? I'm going to draw myself a little x-axis over here. Here's going to be 0, here's going to be pi. Remember, we're doing the integral from 0 to pi of x squared dx, right? So, what are my subdivisions going to look like? How wide? Pi minus 0 over, so where's my first right edge going to be? Pi 100ths. What's my next one going to be? If you say pi 50ths, I'm going to freak out. 2 pi over 100, right? 3 pi over 100. What's the last one? 100 pi over 100, right? Right? And that would be, and we could do this with 1,000, we could do it with 10,000, right? Right? We're going to see a pattern here. Okay, now, so what's my first right edge? My first height? F of, right, because we want the y value. We want the y value, so it's going to be f of pi over 100 times pi over 100 plus, let's do the next one, f of 2 pi over 100 times pi over 100. How about that? Do one more. F of 3 pi over 100 times pi over 100. Now remember, we got our little x-axis here. I don't even need the curve up here, but these would be a bunch of right rectangles. There would be 100 of them in there. Okay, what's the last one? Dot, 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 dot. 100 pi over 100. Now, notice that I used right rectangles, and that's what I said before. The nice thing about right rectangles is they end right here at the right edge. Okay, and that makes it nice. Okay? All right. So, what was the next step we did then? Write our sigma notation. So we got I equals 1, 2, 100 this time, right? Because we're going to add up 100 things. We're going to add up 100 right rectangles, but we're not really going to add up all 100. And then what's going to be in here? F of I pi over 100 times pi over 100. There's our height times our width. Height times our width, right? The only thing changing is that top number. Okay, what do we do next? We took it out of the F notation. It's just because listen, the function might not be as easy as x squared. It might be sine of x. I mean, we're not going to run into those, but it could be sine of x plus e to the x, right? And so this would just get way too messy up here. The pattern would be hard to see. So it's easier to just do f of, get the pattern, and then here do our f of German shorthand, right? F of German shorthand means put the German shorthand in for the x. So we're just going to take I pi over 100, put in for the x. Now it's easy, it's just x squared. Remember, sine x would be sine of I pi over 100, or whatever, right? We're plugging this into the function. So we're getting sigma, I equals 1 to 100. It'll be I pi over 100 squared times the pi over 100. So all I did was take it out of the F notation, plug that into the function for x. And now we want to get this constant out of here. So the same thing. This is I squared, pi squared over 100 squared, right? I'm just going to leave it 100 squared for right now. And then I got this pi times 100, right? So that means I can take, let me come over to here now. So what do I got? So all these constants I can take out. What's that going to be? Pi cubed over 100 cubed. Okay, and then what's in here? The I squared. So I got I equals 1 to 100. Now you're not going to have to do this from scratch in your homework today, but in the homework actually it's in an LH packet, an older LH packet we have, and there's a series of homework problems that are going to lead you through these different steps we've been doing. You're going to find some sigmas, then you're going to do this, blah, 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 and then you're going to go and you're going to do the summation formulas like what we're doing here, but it's going to be broken up into different parts for each of the signs. Okay, so now we get to here. What was sigma I squared again then? So you're going to get pi cubed over 100 cubed times, and now we do our summation formula for sigma I squared, right? What's your sigma formula for sigma I squared? It's n times n plus 1 times 2n plus 1 all over 6, right? So what's that going to be? 100 times 101 times 201 all over 6. Okay, crank that thing into your calculator, see what you get. Give me the fraction and then give me the decimal. Six, 8, 3. Oh, sorry.
I got 6, 7, 6, 7 times pi thirds over 2. Or pi to the third over 2.
Say that again.
6, 7, 6, 7 times pi cubed over 2.
I got that over 2,000.
That's way too big.
I got 6, 7, 6, 7 pi cubed over 20,000.
Over how much? Yeah, are you guys doing the 100 cubed here?
Oh, I thought you just wanted the 100.
No. I want this whole thing multiplied together. I want this whole number here. So Emily, what'd you have?
6, 7, 6, 7 pi cubed over 20,000.
Yeah.
That sounds better.
That's right.
Now give me that as a decimal. How much? How much was this exactly? Remember, it was pi cubed over 3. What was pi cubed over 3?
10.335.
Now, does it make sense that we still are a little too big? Because they're right rectangles. So that, right, and we looked at this picture here, the right rectangles are going to be a little bit too high. But if we have 100 of them, that's pretty good, right? That's pretty close. Okay, see, and that wasn't bad for writing it. It was pretty quick for doing 100 of them, right? That was pretty quick for doing 100 of them. Now we can use our calculator to do this sigma. Okay, so how many would be the best to do them? Infinite. Man, we got just enough. So here we go. We're going to do n rectangles. Not 4, not 100, but we're going to do n. So we're going to start at 0. We're going to go to pi, and we're going to divide that out into n subdivisions. So how wide is each one? Pi over n. Never forget this formula. The formula is b minus a over n. So b minus a in this case would be pi minus 0 over n. So it was pi over 4, then it was pi over 100. Now it's going to be pi over n. So when you see on your homework, when you see these things written out with n's, that means there's n subdivision, an unknown number of subdivisions. So what's my first right edge going to be? But do you see, do you feel how this is the same every problem? What's this first one going to be? Pi over n. What's the next one going to be? 2 pi over n. What's the next one? 3 pi over n. And what's the last one? N pi over n, right? Which of course simplifies to pi. 1 pi over n, 2 pi over n, 3 pi over n. And what do you suppose we're going to have inside of our f? In our sigma? F of I pi over n, right? It's 1 pi over n, 2 pi over n, 3 pi over n, but let's write it out. So what's my first right edge? My first right height? F of pi over n times my width, pi over n, plus f of 2 pi over n times pi over n. We see the pattern. Let's go to the last one. The last one's going to be f of n pi over n times pi over n. We can see our pattern. Let's write our sigma. I is going to go from, this is so cool, I know where, but that's because I know how this is going to end. I equals 1 to n f of I pi over n times pi over n. What's the next step? Take it out of f notation. Remember, this is x squared, 0 to pi. There's our f right there. We know the final answer is supposed to be pi cubed over 3, right? That's supposed to be the actual area. So we're going to take it out of f notation. So we got sigma I equals 1 to n. What do we got? I pi over n squared times pi over n. So now what's I pi over n squared? I know I'm writing, you guys are writing furiously. It reminds me of some of the college classes I took when the professors just be filling the boards all around the room. Writing like crazy. Trying to keep up. Okay? So what would this be? This would be I squared pi squared over n squared times pi over n. So when we write this sigma, we're going to pull out, what are the constants here? Pi cubed over n cubed. N is a constant here. N is the number of subdivisions. So n is a constant, but I is not. So I squared will be in there. So we get I 1 to n. Okay, so now we use our summation formula. See how this is all the same? What we were doing before? Now we got a summation formula. Now we don't have a summation formula. This function would have been sine of I, right? This only works for cubed and squared, but it's going to prove our point. So that's good enough. So what do we got? What's sigma I squared? N times n plus 1 times 2n plus 1 all over, whoops, yeah, I'm in cubed, 6. Now, this time I don't have anything to plug in for n, do I? Okay? Now, here's the thing. when we distribute this out, right, this is going to be, I don't need to know the whole thing, but what's the highest power going to be? N cubed? Isn't it going to be 2n cubed? Because once you have a 2n times an n times an n, you're going to have 2n cubed plus a bunch of other stuff. N squareds, n's, whatever. Right? Okay. It's going to be a big kind of mess. Right? But, now let's think about what we're trying to do. How many rectangles do we want to do here? How many? An infinite number. N is our number of rectangles. So, Will, ask the question you asked earlier today. Are we going to be using limits? Yes, we are. Right now, what we'd like to do with this thing is do what? The limit as n approaches infinity is what we want to do. Oh man, I love how this comes together. Look at this. What happens here as n goes to infinity, especially on this top part? When n gets really big, the cube, the high powers dominate. The n squared, the n, the other stuff up here, doesn't matter. So what do we end up with on top? We end up with 2n cubed pi cubed over 6n cubed. Oh my goodness. What's going to happen? Pi cubed over
So this was worth 4 hours of sleep and that's
you guys only get to see it once. I get to do it twice today and every year for like 20 years.
It's unbelievable. Is that just coincidental? Or did you know?
You obviously knew it was gonna happen.
Look at that. The area under the curve, by definition, this is going to be our formal definition, so let's back up here a minute. Well, we did the derivative at one point. We didn't know how to do the derivative at one point, right? So we said, but we do know how to do the derivative at 2 points. So let's do 2 points, and how could we get the derivative, how could we estimate it? Very first day of class, we said, well, get points really close together, right? Pick 2 points, or a lot of you said pick a point on one side and a point on the other side. Do this whole 2 points. Let them get closer and closer together. Okay, that's an approximation. How do we invent it? Let them get closer and closer. How can we get exact? Let them get infinitely close, right? Let the 2 points become 1. That's the idea of a limit. That was the limit as h approaches 0. So that was the definition of derivative. The limit definition of the derivative. F of x plus h minus f of x all over h. Limit as h approaches 0. We use a limit. Okay, this is its equivalent here for area. We don't. This is why most books, actually, a lot of more traditional books, start with their integral talk with this before they get into antiderivatives. Now, I actually like how our book did. The downside to how our book does it is some of this seems anticlimactic because you're like, I already know how to do this antiderivative, right? I already know how to do this definite integral. I already know the answer is pi cubed over 3. And so you're like, well, why do we have to go back to this? So, but I still like how we do it because we can now know that that is the answer. But the bottom line is we said, okay, we don't know how to do the area under a parabola. It's not a geometric shape, but you know what we do know how to do? Rectangles. We can do rectangle areas, right? So this says, okay, how can you get the area under the curve? Well, do 4 rectangles. Well, that's not very good, so let's do 100 rectangles. Well, that's better, but it's not exact. How can we get exact? Well, 1,000 or 10,000. Well, what can we do? Infinite, right? We can do an infinite number of rectangles. That's what we just did. So the definition of the integral then, the definite integral, is that the definite integral, the area under the curve, can be defined as the limit of adding up an infinite number of rectangle areas. If we can add up an infinite number of rectangle areas, we've got the area under the curve. And that is what that leads to. Now, how useful is it? Not that useful. Fundamental theorem part 2 is way more useful. Okay? And approximation techniques like doing 50 or 100 rectangles and putting it into our calculator, being able to do this pattern, is going to be what we'll do for ones where we can't do the antiderivative, right? This was more theory. Okay, great thing to do on a Friday morning when it's snowing. This was more theory, okay? But here's what it leads us to is this right here. The formal definition of a definite interval. Okay? And so if it means adding up an infinite number of rectangle areas, remember we called that a Riemann sum. A Riemann sum is adding up rectangle areas. So the definite integral is basically an infinite Riemann sum. Okay, so the definite integral, the integral from a to b, f of x dx, is the same as doing the limit as n goes to infinity, sigma I equals 1 to n. And what are you adding up? You're adding up rectangle areas. F of c sub I, remember we said that was our sampling point, might be the right edge. We did the right edge today, right? Our sampling point, our c sub I was the right edge. So it was x1, x2, and so forth. Okay, but it could be midpoint, could be left. We could have done it with any of those rectangle areas. And then delta x is the width. Okay? Now, do those look alike a little bit? Do you see what the dx, what happened to the dx? You know, we talked about where did the dx come from? When we do, think about this now. When we talk about derivative, we use the notation dy over dx. But where does that come from? It comes from slope, right? What is slope? Change in y over change in x, right? But if the 2 points become 1, what's your delta x if you only have 1 point? 0. What does your width of your rectangle become if you have an infinite number of them? Your width becomes 0 too, right? Now, there is one little technicality on this. Remember I said Riemann sums don't have to have equal widths. They can all be different. So technically, it's not totally correct to just say your limit if your rectangles go to infinity. Because you can have one fat rectangle right in the middle that never changes, and all the rest of them get littler and littler for infinity. You can have an infinite number of rectangles and not get the exact area because that one fat one doesn't change, right? I mean, that would be it. We're assuming here that all the rectangles widths go to 0, right? But that's why this dx ends up just kind of hanging out here and not really doing anything, because when we have an infinite number of rectangles, the delta x, the width, kind of goes to 0, right? And it just be, but you can look at that, f of x dx, I mean, you can kind of see. Now all of a sudden, this takes on, or should take on, new meaning for you. When you see the integral of f of x dx, I would hope now you see rectangle area. I would hope you kind of see height times width, height times width, height times width, right? And if this was a rate problem, think of it this way. I'm going to get this in under the y. If this was miles per hour, you can now think of the dx as actually having units. Wouldn't the delta x be your hours? And so doesn't it make sense that when you do the integral of miles per hour, you end up getting miles? Because it's kind of like you're doing miles per hour times hour, right? So now all of a sudden, that dx takes on a little new meaning. Doesn't change how we do the problems at all, but that's where that dx comes from. It comes from that width, that shrinking width. Okay, now, if I ask you about this on the quiz, I might ask you a question about this. Why is this the area under the curve? Well, these 4 things are, I think, the important parts of it. This says you're adding up, this is the height of a rectangle, this is the width of the rectangle. When you multiply it, that's the area of a rectangle. The sigma adds them up, and the limit tells you you're going to add up an infinite number, right? I think you should know all the parts of this and how that gives you that. Just like the definition of derivative, I want you to know that was slope between 2 points. Okay, pull out your old LH packet. I'm sorry, Bill's been ringing. Your old LH packet. I'm talking. You'll recognize it because it's the one that's got sigmas on the very front page. It's the sigma from before. It's 279. Okay, the front page is 279, and it's got some sigmas on it. Okay, your homework is 1 through 8, 9 through 33 odd. 1 through 8, the front page, 9 through 33 odd on LH page 279. Now, it's not going to be as hard as it looks when you're going through it because, I mean, it looks kind of confusing, but basically you're going to expand some sigmas, simple little sigmas. You're going to write sigma notation, but they're written in nice form, so they're pretty easy. And then the last set of exercises, you're gonna go through that last bit we just did, where you're gonna have a sigma, you're gonna use your summation formulas, and then you're gonna let n go to infinity, high powers dominate, cancel, kind of like what we did at the very end. All right.
That was a good one.
Was that all right?